I want to, in this view tube, to discuss the similarities and differences between static and kinetic friction. So first off, friction force, a frictional force, whether it be static or kinetic, is always proportional to the normal force. And you know what the normal force is. So that's something that you can take as given. And this mu, and this is a Greek letter, it's like a U with a long tail to the left on it going down, is represents the coefficient of friction. And there's two cases to consider, either static or kinetic. And so in general terms here, if it's a static case, static means in our situation, static means not moving. It's mu sub s, so that would represent the coefficient of friction for static, and mu sub k would represent the coefficient of friction for kinetic. And what's always true is pretty much is that the static coefficient of static friction is bigger than the coefficient of kinetic friction. Okay, so now that is the real life interpretation of that is that it takes a greater force to get something moving than it does to keep it moving. So keep that in mind as a real world example. So in this example, what we're going to do is we're going to assume that mu sub s is equal to 0.4 and that mu sub k is equal to 0.2, and we're going to take a mass of 1 kg. I'm going to use easy numbers, in which case 1 kg would have a weight of 10 newtons. And so here is a scenario where we have the mass on a level surface. A little bit later we'll talk about a plane, in which case the surface is not level, but for the current case it will be level. And then there will be a force applied, as shown here to the left, CW, that would be me, on M. And so a full force diagram, or a free body diagram if you will, is going to consist of four forces: the downward mg, the upward normal force, the force of CW on M exerted horizontally to the right, and then a resisting frictional force, be it static or kinetic. And we'll outline the differences here as we go. And then here's the coordinate system, so I can bookkeep the signs on my Newton number 2. So first of all, the easy direction to do is Newton number 2 in the y direction, in which case I simply have n minus mg is equal to 0. And thereby I conclude that n is equal to mg. The normal force, in other words, is just equal to the weight. And then the Newton number 2 in the x direction is basically f of CW on m minus mu times n is equal to m times a sub x. And I'm going to just shorten this to f minus mu g is equal to m times a sub x. And so we haven't particularized the mu to mu sub s or mu sub k yet, but we're just about to. Okay, so there's two cases to consider here: static case and kinetic case. So in the static case, basically, the idea of static friction is that static friction will continue to increase up to a maximum amount, and that maximum amount is given by mu sub s times n. So in our case, where I'm saying that mu sub s is equal to 0.4 and the mg, the mass, the weight of this 1 kilogram mass is 10 newtons, that would equate to 4 newtons. And so if the force that CW is applying on M is less than or equal to this force, A sub x will be 0. If it's bigger than that, the mass will begin to move, and in that case we will transition to kinetic friction. Okay, so case number 2 is kinetic, and in that case let's assume that the force that CW is exerting on the mass is larger than 4 newtons, because in that case a sub x is going to be equal to 0. But since now you have relative motion between the mass and the surface, we now must use a smaller coefficient of friction 0.2. This is a fairly good modeling of what happens in real life. Okay, so for example, let's say that CW was exerting a 5 Newton to the right force on little m. And so in that case, our Newton number 2 would be, just to rewrite it here, but with now mu sub k in used for mu instead of mu sub s, because we're now in a region where we've exceeded the maximum static frictional force. If I solve this equation for a sub x simply by dividing both sides by m, and then I put my values in, so I'm assuming 5 newtons for F of CW on m, and mu sub k times the weight is going to be 0.2. That's mu sub k, the coefficient of kinetic friction, times 10 newtons divided by 1 kilogram. And that's 5 minus 2, which gives me 3 in the numerator, divided by 1 is 3 meters per second per second. Okay, so the critical points here in this explanation are that friction is always proportional to the normal force. The proportionality constant is the coefficient of friction. The coefficient of static friction is always bigger than the coefficient of kinetic friction, and that static friction increases up to a maximum given by mu sub s times n. Up to that point, the object does not move. Beyond that point, it starts moving, and then kinetic friction kicks in.